Today we begin the chapter 16, which is electric charge and electric field, a very interesting chapter. And if you can look at the figure here, this Coulomb has acquired a static electric charge either from passing through hair or being rubbed by a cloth or paper towel. The electrical charge on the Coulomb induces a polarization in scraps of paper and thus attracts them. So the other picture where you see a child going through a slide, the static electricity from this plastic slide causes the child's hair to stand on one end. The sliding motion stripped electrons away from the child's body, leaving an excess of positive charge which repels each other along each strand of the hair, so causing repulsion. So we will be talking about several types of charges that we know about. We'll be talking about static electricity and conservation of charge and many other things in this chapter. So when Benjamin Franklin demonstrated that lightning was related to static electricity, he made a connection that is now part of the evidence that all directly experienced forces except the gravitational force are manifestation of electromagnetic force. We will be soon talking about it in other chapters as well. So we will be covering these topics and some of them will be covered briefly. For example, we'll do the theoretical form of Gauss's law, though not part of your course that I have given you the outline, but we may go over just for the conceptual part. But we definitely are going to be solving problems on Coulomb's law, electric field, and very basic problems on electric charge in an atom or generally the charge on a certain object. So what is static electricity basically? And what does it, what do we know about the conservation of charge? So here we will define electric charge and describe how the two types of charges interact. And we will also describe the three different situations that generates static electricity. And by the word static, we mean charges at rest. And then we'll go ahead and dive into the law of conservation of charge. So what makes a plastic wrap cling? It's the static electricity. And not only are applications of static electricity common these days, its existence has been known since ancient times. The first record of its effects dates back to Greeks, who noted more than 500 years BC that polishing amber temporarily enabled it to attract bits of straw. So the very word electric derives from the Greek word for amber, which means electron. And also, many of the characteristics of static electricity can be explored by rubbing things together. Rubbing creates the spark you get from walking across a wool carpet, for example, and static cling generated in a clothes dryer and the attraction of straw to recently polished amber also result from rubbing. So basically, when we rub objects together, then one of the object gets a positive charge, which is it is deprived of electrons, and the one that becomes negatively charged receives the excess of the negative charge, so making it thereby negatively charged. So if you bring a plastic ruler, if you rub the plastic ruler with a cloth or paper towel and then bring it to bits of paper, it starts clinging to it. For the very reason that the transference of electrons takes place. And then we talk about a very important part. It's the two different types of charges. Charges comes in two types, a positive and a negative charge, just as we know that like charges repel and opposite charges attract. So here in the picture you are able to see the same phenomena exhibited, where you see that two charges are getting repelled, where negative and negative repels and positive repels, while as the negative and positive attract. Basically, the two rules that you will remember is about electric charges is going to be like charges repel and unlike charges attract. The effects of static electricity are explained by a physical quantity that was not there before, introduced, and now we call it as electric charges. The force between the two charges basically decreases with distance. We will talk about it during the Coulomb's law. We'll talk about the effect of force on the two charges. And how do we know there are two types of electric charges? When various materials are rubbed together in controlled ways, certain combinations of material always produce one type of charge on one material and the opposite type of charge on the another. So by convention, we call one type of charge positive and another as negative. There is a particular triboelectric series where we know that when we rub silk with an ebonite rod, silk will get a certain type of charge and ebonite rod will get a different type of charge. So it's all tabulated. Since the glass and silk, for example, when glass is rubbed with silk, the glass becomes positively charged. So rubbing glass with silk produces an effect where the glass becomes positively charged and the silk becomes negatively charged. So that means the silk has been ripped off the glass has been ripped off its electrons, which are dumped on the silk. And so we have this classification, and scientists have been able to give us a listing of which object, when rubbed with the other, will be able to give us the electrons or the protons, or the positively charged particle or the negatively charged. So Franklin wrote in his, we have a major contribution by Franklin in the study of electrons and protons, and he talked in his letters and books that he could see the effects of electric charge but did not understand what caused the phenomena. Today we have the advantage of knowing that matter is made up of atoms, and that's when it became very, very clear how our atomic structure is done. So we have more information now because of the advantage of knowing the normal matter is made up of atoms, and the atoms contain positive and negative charges, usually in equal amounts. So electric charge is conserved, means that the net amount of charge always remains same. So if you are rubbing an object with the other object, so you have not created any new charge, you have just transferred the charge from one object to another object, but the total charge in the nature is conserved. So whenever a certain amount of charge is produced on one object, an equal amount of opposite charge is produced on the another object. So that's what it means. The positive and negative are to be treated algebraically. So during any process, the net charge is produced. The sum of the two charges will always be zero. So that's what is the law of conservation of electric charge. And no net electric charge can be created or destroyed. We can only have transference of charge. So this figure over here is a very common figure of showing atomic structure, which shows a simple model of an atom with negative electrons orbiting around the positive nucleus. The nucleus is positive due to the presence of positively charged protons, and there are other entities in the nucleus, that's neutrons, but they are chargeless quantities. And nearly all charge in nature is due to electrons and protons, which are the two of the three building blocks of matter. So if we call three building blocks of matter, one is proton, one is electron, and one is neutron. So neutron being neutral, carrying no charge. Other charge carrying particles are observed in cosmic rays and nuclear decay and are created in particle accelerators. So if you have learned about CERN in Geneva and all, you have particle colliders and all, where experiments have been conducted to create antiparticles as well. So for which they need to be a lot of energy is released when a particle and an antiparticle combines. So that's why they are done in a special laboratories, mostly underground. Such type of experiments cannot be conducted in a normal lab. So, and the charges of electrons and protons are identical. And so, for example, the charge of one electron, which was determined in the lab, is 1.6 cross 10 raised power minus 19 Coulomb. Coulomb is the unit of charge named after the scientist Coulomb, Coulomb. And the magnitude of the charge on electron is 1.6 cross 10 raised power minus 19 Coulomb. The same amount of magnitude of charge is seen for the proton also. The charges are same for both of them. If we don't put magnitude, the charge on electron is negative and the charge on proton is positive. The mass of electron is less. Mass of electron is 9.11 cross 10 to the power of minus 31 kgs. And while its mass of proton is 1.67 cross 10 raised power minus 27 kgs, which shows us that the proton is heavier than electron. So within the nucleus we have protons, and protons can be broken up, and they form quarks. The three quark charges add up to, in this example, we see how one proton charge has been broken into 3 parts, plus 2 by 3, plus 2 by 3, and minus 1 by 3. This is within the nucleus, and which entails and gives us just one one proton. So this is if you add them up, that gives us the sum total as 1 proton. So electrons cannot be subdivided, but it's been found that the electrons seem to have no substructure. In contrast, when the substructure of protons is explored by scattering extremely energetic electrons from them, it appears that there are point-like particles inside the protons, which we call quarks. And these subparticles have never been directly observed, but they are believed to carry fractional charges, as I have shown you over here, like a plus by 2 by 3. The number can change depending on how many protons you have inside that nucleus. And there are continuing attempts to observe the fractional charge directly and to learn the properties of quarks. The research is going on, which are the ultimate substructure of the matter known so far. So the symbol Q is commonly used for charge, and the subscript E indicates the charge of a single electron. And just as we said that the magnitude of the electric charge is 1.60 cross 10 raised power minus 19 for both electron and proton. So the SI unit of charge is Coulomb, and the number of protons needed to make a 1 Coulomb charge can now be determined. 1 Coulomb charge. So since we say that the charge is conserved, that we also say quantized. Charges are quantized. That means the number of electrons or protons inside a charge is given by the formula N E, where N is the number of electrons and E can be electron or a proton. E is the charge, single charge, and N is the number of charges inside that particular atom, or so if you want to find out how many charges, how many number of protons are needed to make a 1 Coulomb charge, you can go ahead and do this math. So the Q is the total charge, which is 1 Coulomb, and charge on, we have to find N, while as E is, if I find the magnitude of E or QE, you could just say QE, which is where E represents the charge of 1 proton or 1 electron. So that's equivalent to 1.6 cross 10 to the power of minus 19 coulombs. So the math we'll be able to work on the math to get what are the number of protons in there. So 1 Coulomb of charge. So I want to find out how many protons are there, which is just with the help of charge quantization formula. Q is equivalent to plus NE, because we are talking about the proton. So where E is the charge of the proton, or you could also write it as plus N times QE, where we are talking about a positive charge. N is equivalent to Q over QE, where Q is the charge of the proton. This Q is 1 Coulomb over 1.6 cross 10 raised power minus 19 coulombs, which is the charge on the proton. So if you go ahead and work on this math, your N will come out to be 6.25 cross 10 raised power 18 protons in 1 Coulomb of a charge. 1 Coulomb charge is a really big number. We have almost 6.25 cross 10 raised power 18 protons. This is a huge number. So do not underestimate 1 Coulomb. 1 Coulomb is a really big charge. Normally we use charges in the form of millicoulombs, microcoulombs, or nanocoulombs. So milli is 10 raised power minus 3, a micro is 10 raised power minus 6, and nano is 10 raised power minus 9 coulombs. So this is Coulomb. So charges, 1 Coulomb is a really big charge. So normally you'll see when we work on the problems, we'll be doing milli or micro or nano. 10 raised power minus 6 is micro, and generally given by the symbol mu. We'll be touching on this. Nano is N, and 10 raised power minus 3 is milli M. So electric charge in the atom. Atom is electrically neutral because the negatively charged exterior, where the electrons are, balance the charge on the nucleus. So rubbing charges objects by, when we rub the charges, we are actually removing electrons from one to the other. And the one that loses the electrons becomes more positively charged, as we have understood this, the process of charging. Water molecule, the water molecule is actually electrically neutral, but charge is not evenly distributed, and we can try and understand this phenomena of water molecule. It's a very important example. So we have 2 hydrogen molecules here and 1 oxygen molecule here. Oxygen being H2O, there's a binding energy between them. So we will work on defining the water molecule. Basically, normally when objects are charged by rubbing, they hold their charge only for a limited amount of time and eventually return to the neutral state. Where does the charge go? Usually the excess charge leaks off onto the water molecule in the air. This is because water molecules are polar. So that is, even though they are neutral, their charge is not distributed uniformly. Thus the extra electrons on say a charged plastic ruler can leak off into the air because they are attracted to the positive end of the water molecule, which is the hydrogen side. All right. And a positively charged object, on the other hand, can be neutralized by the transfer of loosely held electrons from water molecules in the air. On dry days, static electricity is much more noticeable since the air contains fewer water molecules to allow leakage of charge. On humid or rainy days, it is difficult to make any object hold a net charge for a long time. So that's the story behind if you're wearing a synthetic shirt, if in the winter time you try to take it off, you feel the sparks are flying by. So there are two types of conductors, as we already know. Suppose we have two metal spheres. One is highly charged and the other is electrically neutral. So, for example, a rubber ball and a metallic ball. If we now place a metal object such as a nail so that it touches both spheres, the previously uncharged sphere quickly becomes charged because there's a transfer of electrons. Now that we transfer the charge over it, we are dumping the charge over it. So because it was metal is transferring it. But if we put the wood, nothing is going to happen. So that's because wood is a non-conductor, and nail, for example, in this case, is a conductor. So metals are generally good conductors, whereas most other materials are insulators. Nearly all natural materials fall into one or the other category, but there is one more category which is in between the two, that's called semiconductors. Almost all of our tech, computers and all, is dependent on these semiconductors. From the atomic point of view, the electrons in an insulating material are bound very tightly to the nucleus. So in a good metal conductor, on the other hand, some of the electrons are bound very loosely, and that's why they can easily and freely move. Hence, free electrons cause the conduction of electrons, cause the conduction or cause the motion of electrons, and hence electricity or electrostatics. So there are several ways by which we can charge an object, a neutral object. So metal objects can be charged by conduction. So if I take, for example, if we take a neutral metal rod, which is not connected to any of the, it's not connected to a battery or anything. So no transfer of electrons is happening. When a metal rod is sitting idle, it is neutral. But when we charge the metal object by either rubbing or by bringing it closer to a charged object, the metal acquires the charge. The metal by contact. Okay. Suppose a positively charged metal object. So, for example, this A object is brought close to an uncharged metal object B. So both are metals, and if the two touch, the free electrons in the neutral one are attracted to the positively charged object, and some of those electrons will pass over to it. So since object B, originally neutral, is now missing some of its negative electrons, it becomes positively charged. This process of dumping the charge or electrons, or taking away the electrons and thereby acquiring a positive charge, is called conduction, because we are directly touching the objects. So there is other way of charging as well, which is called induction. For example, in an electroscope, we'll talk about that. Suppose a positively charged object is brought fairly close to a neutral object. So for example, in this case, this is the neutral one, and this is a negatively charged rod that I brought closer to the neutral one, but I'm not touching it. So although the free electrons of the metal rod do not leave the rod, they still move within the metal. So they're able to move back and forth. So what happens If you look at this diagram first, this rod was neutral initially. Then I brought this negatively charged rod close to it. And what happens because of the atomic structure at the top, the negatively charged electrons are free to move in the metals. So they still move within the metal towards the external positive charge. So the electrons move towards this end because of the repulsion created here, because like charges get repelled. So they get repelled towards the exterior end, that is towards this end, as you can see in the diagram. And hence this side is left more positive, which causes the attraction between the two. The electrons are pushed away from this end because of the repulsion. And if you now take away this rod back and move it far away from it, this charge is redistributed on this, and we say that we have charged this neutral rod positively. This is how you can charge a rod by induction. So the steps are, you first have a neutral rod, then you bring a negatively charged rod, and if you want to positively charge this rod, you will bring this close to this. The electrons in this one get pushed towards the other end. They flow to the ground, and once you remove the source of negative electrons away, you can see that it's a standalone. We have a standalone positively charged conductor now. So hence we have been able to charge the neutral conductor by induction, by bringing the negatively charged rod close to it. And non-conductors won't become charged by conduction or induction, but will experience charge separation. So this phenomenon is actually called polarization. If we have non-conductors like a wall, a plastered wall, and so for example, if I want to if you have ever had a balloon and you wanted to stick it to the wall, so you rub a balloon against a sweater or hair and you put it against the wall, you notice that it clings to the wall. The wall is neutral, it's a non-conductor. So how did it get stuck to it? So if the balloon is negatively charged, you must know that there is atomic structure here in such a way the positive end of this will get attracted to this, and the negative end is pushed towards the end. This becomes elongated. If this is the circle, if initially in absence of the rod, they would have had a structure like this. But once we bring a charged object close to the wall or to a non-conductor, the structure becomes more elongated, with the positive charge getting pushed towards the end. In this case, we are bringing a positive rod, so there will be a repulsion to the nearest end, and hence attraction because of the negative charge. So you get an elongated version of this. So more and more, because of this attraction between the positive and the negative, the balloon or any other object will get stuck to the wall. We took the example of a wall. So this another way to induce a net charge on the surface is basically called an polarization. Earthing is the, if you see this sign over here, we call this as earthing. That means the excess charge is dumped into the ground. We use the word earthing. The object is, when we say the object is earthed or grounded, we are sending the excess charge down to the earth, which is a huge reservoir. And we also have an electroscope, which has the electroscope. What is an electroscope? It was the earliest device that can be used for detecting a charge. So for example, we show you, it's actually a gold leaf electroscope. So there is an insulator here, and there's a metal knob here on which we dump the charge. We can either dump directly the charge over here, and this one gets positive charge as well. And the positive charge, due to repulsion, the positive charge is also sent to these leaves, because of which they diverge. Same way, if we get a negative charge rod, the excess negative charge is dumped here, and because of the repulsion, the divergence is seen in the leaves as well. So you can detect charges with the help of gold leaf electroscope. And so if a positively charged, we have more examples of this. We can explain it in a little while. But I want you to understand, I was talking about the millicoulombs, and you have to kind of memorize this thing. 1 millicoulomb is 10 raised by minus 3 coulombs. 1 micro, this strange sign is a micro, it's a Greek letter, which actually means 10 raised by minus 6. N is for nano, which is small, 10 raised by minus 9 coulombs. So when you're solving problems, you want to use this information. And the charge, induced charge on the electroscope. So this is the electroscope that you saw. We are just showing you the symbolic representation of it. The electroscope can be charged either by conduction or by induction. If you are using the conduction, you're directly dumping the charge, and hence the charge, because of the repulsion, the positive charge is sent out here, and the leaves diverge. So you can see that they go ahead and the leaves separate out. The distance of separation increases further. But if I use the induction process, you know what happens to this. The charges closest, because of the repulsion, the positive charge is sent to the ends, to this end, and they travel here and cause divergence, while as this knob stays negative because of the charge separation. And this is a better way of looking at charging by induction. So if we had a metallic ball and I get a positively charged rod close to it, just see how this side, this is the surface charge. The negative charge is coming closer to it. That means there's an attraction, and the positive charge gets repelled towards the other end. In the next step, we connect this side to the ground, so that the electrons from the ground go and neutralize this. So once we remove this, that's the third step, we remove this rod from here, and a net negative charge is induced on the metal ball. So this is one of the way. This is also one of the examples how you can create a positive charge on one metallic sphere and a negative on the other sphere. So in the same process, what we do, we make a contact between the two. We have two spheres and we contact them, and we bring a positively charged rod close to this. So with the result of induction, the negative charge is dumped closer to here because of the attraction, and the positive charge is sent over to the other end. If I now remove this, if I separate them out, there is a net positive charge on this one and a net negative charge on this one. In absence of this, now if I remove this rod, the negative charge will cause the attraction of the positive charge. So now we have a negatively charged ball and a positively charged ball, or a sphere separately induced. This is only for transitory time. This is not a permanent process. It can only stay in this scenario for maybe a few seconds or maybe a fraction of a second, depending on how much of the charge was dumped. So these are only temporary charging that is being done. So that's the difference between electrostatics and electricity. So the electroscope was used in the earlier studies of electricity, and you cannot tell you cannot tell the sign of a charge just by like that, but we do use Coulomb meters to check whether it's a positive or a negative charge. If we know what charge the rod has, we can depict sphere A and B. We cannot see these charges, but we logically know if I bought a positively charged rod closer to the combination of A and B, negative will be attracted this side and positive will go to the other end because of repulsion. And hence we can, in these steps A, B, C, and D, we can create a positively charged metal sphere and a negatively charged metal sphere.